Okay, and then the second hour from here, I got all the way up to 6. I'm going 3 and 3, and then from 6 I went to 9. There's another 3, and from 9 I went to 12. Okay, so in 4 hours, how far did I go? I got 12 miles away from 0, so to the right of 0. Which translates to mean positive 12. So 3 times 4 happens to be positive 12. Okay, so let's look at another one. Let's do 3 times negative 4. Okay, so that says move right at 3 miles per hour, but go 4 hours ago. Okay, this will make sense why I'm creating number lines that look like this once I start explaining this. Oh no, I'm not going to have enough space. Alright, let me fix this real quick. Okay, so if you think about it, here I'm at 0, and I want to go 3 miles per hour, but I'm now going 4 hours backwards in time. So where was I? If I was going to the right, facing 3 miles per hour positive, but we'll go backwards in time, well, what happened? Well, I have to walk backwards for a second. So the first hour, or an hour ago, I was at negative 3. In order for me to be at 0 now, 2 hours ago I was at negative 6. 3 hours ago I was at negative 3, and 4 hours ago I was at negative 12. Okay, so 4 hours ago I would have been starting at negative 12 in order for me it to be at 0 now. So 3 times negative 4 is negative 12. Okay, let's keep going here. Let's do another one. So negative 3 times positive 4 translates to move left at 3 miles per hour, and we want 4 hours from now. Okay, let me set up my number line here. I'm just going to pause it so you can kind of see the fruits of my labors instead of watch me actually make a number line. Okay, so if I start at 0, and now I'm going to the left 3 miles per hour, so in that first hour I got to negative 3, and the second hour I got to negative 6, third hour I got to negative 9, and then the fourth hour I got all the way to negative 12. So negative 3 times 4 is negative 12. Okay, let's do one more. Let's do negative 3 times negative 4, which we're going to translate to mean we're going to move left at 3 miles per hour, but I want 4 hours ago. Okay, again, let me pause it so I can create the number line. Okay, so even though I'm still starting at 0, and even though I'm facing that direction, I'm thinking to myself, 4 hours ago, I started somewhere and I ended up at 0. So where did I have to start off at? So an hour ago, I would have been, keep in mind I'm facing this way, so an hour ago I would have been at 3. 2 hours ago I would have been at 6. 3 hours ago I would have been at 9, and then 4 hours ago I would have been at 12. So I had to have started at 12 in order to end up 4 hours later at 0, heading to the left at 3 miles per hour. Okay, so negative 3 times negative 4 happens to be positive 12. Okay, so let's look at what the formal definition of integer multiplication would be considered. So we're going to let A and B be any integers. Okay, and then we're going to define a couple of statements. Statement, first one, then if either A is greater than or equal to 0 and B is greater than or equal to 0, then A and B are actually whole numbers, with product AB. Okay, so we kind of break these up into cases and we say, okay, so one way to think about this, if A and B are both positive numbers or 0, then we can treat them like they're whole numbers and the product would simply be A times B. Okay, or what else could we say? What if I know that A happens to be less than or equal to 0 and B happens to be less than or equal to 0? So I know A and B both are either both 0 or both negative. In that case, then we define the product AB to be the absolute value of A times the absolute value of B. Okay, so in other words, a negative times a negative is actually a positive number, and we can pretend they're both positive and multiply them together. Okay, and then we look at this scenario where one of them happens to be negative and the other one is not. So if either A or B is less than 0, while the other is greater, okay, then we define the product AB to be the opposite of the absolute value of A times the absolute value of B. Okay, so sort of hit all three cases. Any two integers we multiply together will fit into one of these three scenarios. Now, honestly, we can just use our common multiplication rules, things that we're very familiar with, but in a very formal language sense, this is what we define as integer multiplication. Okay, so under property rules, the following properties are still held as true underneath integers. So the set I of integers has the following statements true about it. And we are assuming that we're going to let A, B, and C be elements of the integers. So I'm going to, in various statements of these properties, I'm just going to tell you right now that I'm assuming that the three numbers that I'm going to refer to are integers themselves. So we have the closure property of multiplication, which says if A and B are elements of the integers, then AB is also the element of the integers. And AB is a unique integer. We have the commutative property, which says A times B is equal to B times A. We have the associative property, which says if I'm multiplying three things together, I can rearrange the order any way I want. We have the identity property of multiplication of integers, which says that there exists a number 1 such that 1 times A is equal to A times 1, which is equal to A. Now, again, in number sense, that's just common sense, that 1 times anything, but we're saying that there has to exist this magic number 1 that has the following condition, that if you multiply it by any number, it keeps the number the same value. We have the distributive property, which says what we what we're familiar with, that A times the sum of B plus C, we can distribute that in. So AB plus AC. And we can also go reverse. So if it's B plus C with A on the other side, that we still translate that to AB plus AC. And I think that would be one to emphasize to students because they seem to freak out if it's on the other side of the parentheses. And then we have the zero property. Okay. And the zero property says that there exists this number 0 such that 0 times A is the same as A times 0, which simplifies down to that 0. Now again, I know that's common sense in numbers. We understand that 0 times anything is just 0. But what this property states in formal language is that there exists something like unto 0 that if I multiply, I end up getting that same original something back. Again, common sense, 0 times anything is just 0. Okay, so with these property rules, and especially the distributive property, that also allows us to define specifically what it means if we are distributing across an expression that has a subtraction in it. So let me kind of do both directions of this. This is what we would blankly call as a distributive property, and it's true. So we still get AB minus AC in both cases. But that allows us to now work some examples that illustrate this. So I'll kind of do two of them. One of them hopefully is very familiar. Alright, so in this case, negative 3 times x minus 2, using that first statement, I get negative 3x minus negative 3 times 2. So negative 3x minus a negative 6. And from earlier, we have that add the opposite rule, so negative 3x plus 6. So what that simplifies down to. The other expression, if I distribute that, I get a squared minus ab plus ab minus b squared. And notice the middle terms can cancel out, so I get a squared minus b squared. Okay, this is a nice foiling pattern or distributing pattern called difference of two squares that we should be very familiar with by name. Anyways, difference of two squares.